Hello, Lamai. This is our second day on S block, right? S block right? So today we are going to discuss about the reactions with S block metals, right? Today our discussion is going to be about the reactions involved in the S block metals, right? So let's begin, right? What we are going to discuss today, right? So that is all about this, Lamai. So we are going to discuss about reactions of S block metals. Right, in your tute, that is all about the page number 6, right? So first let's have some idea what kind of reactions we are going to discuss with this section, right? When it comes to reactions with S block metals, basically those comes under, we can categorize the reactions of S block metals under two categories, under two sections, right? The S block metals react with elemental gases, so like elements, right? Elemental gases. So like sodium reacting with O2, which is an elemental gas. So sodium react with N2 gas, sodium react with H2 gas, right? Those are the examples for S block metals reacting with elemental gases. Let's take the magnesium as an example. Magnesium with O2 gas. Magnesium with N2 gas. So magnesium with H2 gas. This is one kind. Reaction of S block metals with elemental gases. These are the first stuff we are going to discuss with this topic, right? Then we have to discuss about the reactions of S block metals with compounds. Compounds are the ones which are constructed with two or more than two elements. So only one element, one type of element is appearing, one type of atom is appearing. Those are considered as elements. If more than one type of atom is appearing, right, then we call them as compounds, right? So we will react the S block metals reactions with these compounds, right? So let's say H2, it's another compound. Then discuss about the reactions with NH3 as well, right? Reactions with compounds. So these are the major two categories we'll discuss with this section. The reactions of S block metals with elemental gases, with elements, and reactions of S block metals with compounds. As compounds, normally we consider the hydrides, group 17 hydride, this one is kind of group 16 hydride, the oxygen hydride, and this is kind of a group 15 hydride, right? S block guys reactions with compounds, right? Those are the major two categories, right? Right, this is with, so we have another, right? This is with elemental gases, and this is with compounds, right? When it comes to reactions of these with elemental gases as well as compounds, right, we are expecting kind of redox reactions to occur. That means we are expecting kind of change in oxidation states of these reactants, in these reactions. So what is the logic there? So the logic is this, Lama. Normally, S-block metals are considered as active metals, right? Normally comes under the active section at the activity series. So when it comes to the metals of the activity series, the top part, the top few elements are actually coming up as S-block elements, right? Those are the active metals. So in the activity series, the active metals are the most keen metals to get oxidized. So they are keen to be as positive ions. When the sodium is get to oxidize, it will convert to Na plus, magnesium Mg2 plus, potassium K plus, like this. So that S-block elements are very keen to be as positive ions in nature. S-block metals prefer to be as positive ions in nature. Normally, you observe the sodium as salts in nature, NaCl, sodium sulfate, in minerals as well as in seawater, you can observe those things. The potassiums as well, the magnesium sulfate, like that, magnesium chloride. So S-block elements tends to be as positive ions in nature, as those are very keen to be as positive ions because those are coming under the active section of most of the terms, guys coming under the active section of the activity series, right? Very keen to get oxidized and be as positive ions. So that in these reactions as well, they tend to get oxidized and be as positive ions at the product section, right? That is what happens. So if you are considering a reaction involving a S-block metal, definitely that is going to be a redox reaction. If the S-block guy is as a metal at the elemental form, definitely, right, some redox reaction will occur, right? So in these cases, right, in these cases, even these, all of these cases, S-block thing will appear in the elemental form. So in a reaction, if the S-block species appearing at the elemental state, definitely those reactions are considered as redox reactions. Redox reactions. Where the S-block guy will get oxidized to come up as positive ions, and something from here should get reduced. See the products here. Magnesium react with O2 gas. Magnesium react with O2 gas. So what happens? Magnesium get oxidized as Mg2 plus, and the oxygen here will get reduced to O2 minus, right? Magnesium will get oxidized to Mg2 plus, oxygen will get reduced to O2 minus. So the oxygen will normally get reduced to O2 minus, right? No other ion, right? Normally tends to get reduced to O2 minus. Normally they prefers to come up with the, when they are coming up with the right monoatomic form, monoatomic anions, when they are coming up with the monoatomic anions, the nonmetals, they normally coming up with the Nobel gas configuration, the ion with the Nobel gas configuration, right? When nonmetals are coming up as monoatomic ions, a single atom is there. When they are coming up as monoatomic ions, they tends to come up as come up with the noble gas configuration. So if nitrogen is to get reduced, it will coming up as N3 minus. Hydrogen to get reduced, it will coming up as H minus. Monoatomic form, monoatomic anion, they will come up with the noble gas configuration. The hydrogen's nearest noble gas is helium. To gain that configuration, hydrogen needs 1 electron, that is why the H minus. The charge is -1. Nitrogen is the 7th element. Its nearest noble gas is the neon, the 10th element. That means you need to come up with 3 electrons. You have to add 3 electrons to nitrogen to come up with that configuration. That means nitrogen as a monoatomic anion coming up as N3 minus. 3 electrons are needed to gain the noble gas configuration of neon. That means N3 minus, like that, right? So magnesium will get oxidized to Mg2 plus. Nitrogen will get reduced to N3 minus. Here the magnesium will get oxidized to Mg2 plus. So when it comes to S block lamai, group 1s always get oxidized to 1 plus ions, while the group 2s will always get oxidized to plus 2 ions. That is how they achieve their noble gas configurations, right? Those are normal, the group 1s. So normal lamai, when it comes to monoatomic ions, right, of S block as well as the non-metallic monoatomic anions, they tends to achieve the noble gas configuration. They tends to release all the electrons in their valence shell when they are forming cations, and they tends to gain the remainder of electrons to achieve the noble gas configuration when they are forming anions, right? Okay, so Mg2 plus releasing both the electrons at the valence shell of magnesium, right? So the compounds are going to be then Mg2 plus and O2 minus. It is magnesium oxide. Just explain the valencies. Mg2 plus N3 minus, magnesium nitride, Mg2 plus H minus, magnesium hydride. Mg2 plus H minus, then that's MgH2, right now, magnesium hydride. Okay, so it is very easy to come up with the products, right? Magnesium react with O2 to form the magnesium oxide. You can't have any other compound, no, any other product, right? When magnesium reacting with O2, no? If the magnesium is reacting with O2, the product side also should contain the magnesium atoms and oxygen atoms only, right? The mass conservation, right? If only the magnesiums and oxygens are appearing at the left hand side, the right hand side of the equation should also come up with the magnesium and oxygen, right? So only possibility is then the magnesium oxide. You can't have any other product containing hydrogen or something like nitrogen or anything, right? Okay. So magnesium oxide. Magnesium with reacting with N2 will give you the magnesium nitride. So monoatomic form, basically as the elemental form of this block guy is used. Definitely redox reactions should be considered. Magnesium guy oxidizes and connects with the anion of the non-metal, right? So this guy oxidizes and connects with the O2 minus. Here connects with the N3 minus, the anion of the non-metal. Here the H minus. This guy oxidizes. Redox reactions, right? Right now, this is how we are supposed to predict the products. Electrons are released from here to here. Right, okay. So you can balance this up, right? Alright. Let's discuss about the reactions with compounds as well. Right, definitely your elemental form of this block guy will get oxidized. So to magnesium 2 plus. So when it comes to these compounds, as these compounds are with some negative ion as well, this S block guy, after it oxidizes to to the ion Mg2 plus, that will connect with the anion of the compound. So Mg2 plus connecting with the Cl minus will give you the MgCl2. right? Then cation of the compound will reduce. If someone is to get oxidized, some other thing should get reduced, right? Should get reduced. So H plus here will get reduced to H2. So all are redox reactions. If S block element is used in a reaction, definitely those comes under redox reactions. As H block elements always prefer to be as the cationic form, As products, always they tends to be as cationic form. So here, magnesium will oxidize to magnesium 2 plus and connect with the anion of this stuff. So the H2O can be considered as H plus and OH minus, or one can consider it as 2 of H pluses and O2 minus. Two forms of stuff are there with the H2O. So Mg2 plus, when it is reacting with hot water, it prefers the OH minus. When it is reacting with steam, the H2O gas, it prefers the O2 minus. We'll discuss those things under that section, right? How to come up with the correct form, how to choose the correct form, whether the magnesium 2 plus is connecting with the O2 minus or the OH minus, how to choose that thing, we'll discuss later, right? So anyway, when this Mg2 plus is to react with, it will combine with actually the anion of this stuff, right? So let's consider this as hot water. In the hot water situation, magnesium 2 plus connecting with the anion OH minus, Mg2 plus and OH minus, MgOH2, and this H plus here will get reduced to H2. Right? This is how we are supposed to predict the reactions, the products. Because these are, yes, magnesium will get oxidized to magnesium 2 plus and connect with the anion of this thing. So NH3 also can be considered as a combination of H plus and NH2 minus, like this, or 3 of H pluses with the monoatomic form, monoatomic anionic form, N3 minus. Right? Normally in this case, magnesium will connect with the right N3 minus. So we'll discuss the reasons why a specific anion is selected. So magnesium 2 plus, N3 minus, right? N3 minus, magnesium nitride, and hydrogen will get oxidized, reduced to H2. While magnesium get oxidized, hydrogen will reduce here. Right? That is how we are supposed to come up with the products, right? We'll discuss how to choose which kind of form to go with. Few rules are there, right? Okay, we'll discuss those rules. Right? So this is how we should be able to predict the products of a reaction with S block metals. So if you are dealing with S block metals, now the ultimate line is you should come up with some redox reactions to come up with some cations with S block metal, right? And they are right. The other species will get reduced. Right now, the idea is clear. Right. So what happens if S block thing is appearing as a compound? See, those are the first type of reactions we will discuss under this section, right? The second type of reactions. Now let's consider, right? When the elemental form is there, now we will discuss when S block compounds are involved, right? S block compounds are involved. Or one can say compound form if this block guy appearing as a compound. See, let's discuss about these things. So what will happen if you add some water to these compounds? That will be discussed. Let's say you have oxide, so calcium oxide or something, right? Calcium oxide. right? Some kind of calcium nitride S block, guys. Calcium hydride. So we'll discuss what will happen if you add some water, right? So these can be considered as S block compounds, compound form of S block elements. Then which kind of reactions we are preferring to? So if the guys are available as compound form, so the reaction kind is ion exchange. Reaction type is ion exchange. Ion exchange. So see how to predict the product. See, so if the S block guy is as a compound, you have two ions here, Ca2 plus and O2 minus. Here you have the H plus and OH minus. So the products are going to be what? The cation of this thing will connect with the anion of the other species. Anion will connect with the cation. So Ca2 plus and OH minus, Ca2 plus and OH minus, Ca2 plus and OH minus. That means CaOH2, exchange of valencies, right? Plus H plus and O2 2 minus, that is H2, H plus O2 minus, H2O. And we are not supposed to write the H2 at the both side of the equation. In a chemical reaction, we don't write the same species at both sides. So we will omit that thing. So CaOH2 is the product. You think of this, you have Ca2 plus and N3 minus, the anions here. You have the H plus and OH minus here. So cation will connect with the anion of the other species. The cation will connect with the anion of the other species, right, like that. So CaOH2. Then H plus and N3 minus. N3 minus and H plus. N3 minus H plus. That is, see, exchange of valencies will give you NH3. NH3. Right? For this one, is calcium 2 plus and H minus, the ions there. And you have the H plus and the OH minus. So connect, do the exchange of ions, right? Ca2 plus comes with the OH minus, H plus comes with the H minus, right? So calcium hydroxide, H plus and H minus, that is H2. H2. See how we are supposed to predict the products? That is very easy. Yeah? That is very easy. If you are dealing with the elemental form of the S block guy at the reactant side, definitely those are redox reactions. S block guy oxidizes and connect with the anion of the other species. So definitely there should be a reduction as well with the other compound or the element. When it comes to the compound form of the S block guys, if you are thinking of S block compounds, then those are ion exchanges. No need of a redox reaction there because S block guy prefers to be as cations. So the cationic form appears at the reactant side then now. So that, right, no other way to think of reaction other than the ion exchanges. Ion exchanges, right? ඒතකොට ළමයි අර අපේ සිලබස් එකේ ළමයි මේජර් රියැක්ෂන් ටයිප්ස් හතරක් තියෙනවනේ. We are with 4 major reaction types in our syllabus. අර මුලින් කතා කරේ with unit 3. Thermal decompositions, acid base, precipitation, and the redox scale. Right? Thermal decompositions involve heat. Without heating, we are not supposed to discuss about thermal decomposition, right? When it comes to other three types, the acid base as well as the precipitation, those reaction kinds comes under the ion exchange reaction kind. Ion exchange reaction type. Precipitations, always cation of one species will connect with the anion of the other species. Anion of the other species connect with the cation of the other species. That is the way of right, in the products in the precipitation reactions, even in acid-base reactions. NaOH HCl reaction, consider that, right? Na plus of NaOH and the Cl minus of HCl will combine to give you the NaCl, and H plus of the HCl connects with the OH minus of the NaOH to give you the H2O, which is the other product. So products are formed basically by ion exchanges when considering acid-base reactions as well as precipitation reactions, right? Like that. That is a major reaction kind, right? That is a major reaction type, ion exchange kind, right? Then redox reaction. So in S block things, the two major types of reactions involving here are actually redox reactions and the ion exchanges, right? Redox reactions, the idea is clear. When the elemental form is there with this block, the redox reactions are to be considered, and when you are with compounds of S block, definitely those should be coming under ion exchanges, exchange of ions to come up with the products, right? Now, okay, these are two major reaction types, reaction kinds we will discuss, okay, under this section, the reactions of S block metals, right? So that is there in the start of the lesson as the first point, right? In these reactions, S block metals act as reducing agents. See, S block guys get oxidized, killed, about these things, right? Okay. After studying these ones, we'll discuss these things later when the S block guys appearing as compound form, the ion exchanges. But the section which is actually written there, the page number 6 is all about these 6 reactions, right? Okay, now the reaction set එක තමයි අපි කතා කරන් තියෙන්නේ. ඉතින් අවශ්‍යම හරියට තියෙනවා ඔයගේ note එකට දාගන්න. Right? ඉතින් ඔක තමයි අපේ outline එක අද කතා කරන්නේ. Right? Today we are trying to discuss about these reactions mainly, right? Okay. හරි නේද? බලන්නකො අවශ්‍ය දේවල් ලියා ගන්න. Right, ne? Okay. Let's move towards the first subtopic under reactions of S block metals. Right? First, we'll discuss these three things. How the S block guys react with O2 gas, N2 gas, and H2 gas. The reactions of S block metals with elemental gases. That is our first section to discuss, right? Right? Reactions with O2 gas. Right? Let's discuss about this reaction with O2 gas. Okay. Right. So first, let's discuss about the group 1 elements, how they react with O2 gas. Right? Reactions of group 1 elements with O2 gas. Right? It is like this, Lama. All group 1 elements react with O2 gas, right, to produce respective oxide. Right, to produce the respective oxides. That is the first point. Right, you should remember. And when excess of O2 gas is added, when excess of O2 gas is added, and heated. Heating is important. Excess CO2 gas and heating. Then lithium will do nothing more than the producing oxide, but sodium will produce peroxide other than the oxide, and potassium, rubidium, cesium, which are more reactive, will produce, right, peroxides and superoxides other than the oxide, besides the oxides. These are the things you should know, right? Okay. Let's summarize. Let's discuss what it says, right? So, if you summarize the stuff, you can say lithium with O2 gas, it produces only the oxide. Lithium plus O2, right, giving you oxide. Oxide means O2 minus 4. O2 minus 4. So lithium plus O2 minus. So exchange of valences will give you Li2O. Lithium produces only the oxide. Only the oxide is produced by the lithium. No reaction with excess O2. I mean, no specific reactions with the excess O2. Even with the excess O2, you just produce the oxide. Right? But when it comes to sodium, reactivity of sodium is greater than that of lithium. Huh? Reactivity of sodium is greater than that of lithium. Right? Reactivity increases. Huh? Going down, reactivity increases. Last day we had discussed about that. Reactivity of metals is all about ability to get oxidized. Going down as atomic size increases, ability to get oxidized increases. As now your valence electrons are away from nucleus when the atomic size increases. So it is easy to get ejected. Right? So that sodium will react more with oxygen when you are to add some more oxygen and heat it. So with the normal situation, if you are coming up with limited oxygen, sodium will also produce the oxide, but when you have added excess oxygen and provided some heat, right, some excess oxygen and heat, then more reaction, right, more reactivity is possible with sodium, not like lithium. The sodium's reactivity is high, so it will react more with sodium to produce the peroxide, like H2O to hydrogen peroxide. This is Na2O2 peroxide. Not only the oxide will be produced, but peroxide will also produced by sodium if you add excess oxygen and heating. If you had don't add only the just normal oxygen, not in excess and not heated, just the oxide will produce. But if you had added some excess O2 gas, more oxygen, and heated, then you will come up with the peroxide as well with sodium, as its reactivity is high compared to that of lithium, right? The idea is clear now? Right? You can clearly see, right? When producing peroxide, so sodium to oxygen is 1:1 ratio. Here, per 1 sodium, only 0.5. Per 1 mole of sodium, only 0.5 moles of oxygen connected. So here, per 1 sodium, 1 oxygen is connected. Or if you are to balance this stuff, you clearly see the difference. Right? If you balance the stuff, this will be a balance like this, no? This will be balanced like this, no? Right? Sorry, the 4, no? So to balance this one, 2 sodiums. No? So you clearly see, right? Per 1 sodium, only 0.25 oxygens. Per 1 mole of sodium, only 1/4 of 0.25 moles of oxygen is reacted. With this one, with 1 mole of sodium, 0.5 moles of O2 will be reacted. 0.5 moles of O2 will be reacted. So more oxygen will be reacted. Now, when forming the peroxide, so reactivity of sodium is high, able to react with more oxygens, right? Compared to that of lithium. So 1 mole of lithium react with only 0.25 moles of oxygen. Even you are to add excess oxygen and heat. But with sodium, more oxygens have been connected. That means reactivity is high with the sodium than the lithium. When it comes to the potassium rubidium cesium, right? With the normal oxygen without heating, right? Without heating, you only produce the oxide, right? You only produce the oxide, right? But if you are to add some excess oxygen and heating, you will produce the peroxide, not only that, but also superoxide as well. With excess oxygen and heating, you will observe peroxide as well as superoxide. Superoxides will also be produced, right? With the potassium, rubidium, and cesium, right? Superoxide. The form is KO2. The form is KO2, right? O2 minus form, right? O2 minus form, right? Okay. This is oxide, peroxide, and the superoxide, right? Okay. So, what are these oxides, peroxide, and superoxides? Oxide means O2 minus. Peroxide means O2 2 minus. Superoxide means O2 just minus, like that. Okay. So you clearly see 1:1 ratio here. More oxygens have been reacted with potassium, rubidium, and cesium when forming superoxides. So reactivity increases, going down. That is clearly understood with this reaction pattern, right? So these things should be known. Not only this, Lamai, you should know the major product. You should major product out of these two when reacting with excess oxygen. When reacting with excess oxygen, right, both these guys will produce. When reacting with just the O2, only this reaction will occur. When reacting with excess oxygen and heating, both of these reactions will occur with the sodium, and this is going to be the major product. Peroxide is going to be the major product there, right? It's the major product. Product mixture will form where the major product is the peroxide with the sodium with excess oxygen and heating. When you heat potassium, rubidium, when you react potassium, rubidium, and cesium with just the O2, only the oxide will produce. But if you are to react the potassium, rubidium, or cesium with excess oxygen and heating, then oxide, peroxide, superoxide, all the things will produce. Product mixture will be formed where the superoxide is the major product. Where the superoxide is the major product, right? Okay, you should know the major product as well. Major product. Right now. Right? Okay? Clear? Right. So, I write summary here. I write a simple summary here as well. Before that, just copy this stuff, Lama. Just first copy this stuff, and I need some write 4-5 lines of space to write the summary as well. Right? What you need to do is just copy this stuff. Right? Summary कर लिया ना, हम summary का सूत्र लिया ना. Do I have enough space to copy the summary? Right? Okay, I'll draw the summary here. Just write this stuff, and yes, I'll copy some summary here. Right? You need to copy these ones, and this is the summary, right? Summary with excess O2 gas and heating. Right? I'll copy some summary with some tabulated form. Right? Peroxide and superoxide. No? Right? No? Lithium, sodium, potassium, rubidium, cesium. Okay. So lithium will produce the oxide. with excess oxygen and heating, right? All the guys will produce the oxides, right? And sodium will produce the oxide and peroxide mixture, where the major product is the peroxide. Potassium, rubidium, cesium produce oxide, peroxide, superoxide mixture, where the major products are the superoxides, right? That is a summary, right? Right. With this symbol, I used to indicate this symbol to indicate the major product with the excess O2 gas, right? This is summary table, right? So first, write these reactions and put this summary as well, right now. So with this table also you can realize that going down, that the reactivity will increase, right? Okay, reactivity will increase. Right now, that means the ability to get oxidized, right? So when the size increases, ability to get oxidized increases, right? Okay, right, complete the stuff. Right now, okay, let's try to come up with the next section. So this is all about how these group 1 guys, how these group 1 guys react with O2 gas, no? Right. Then we'll discuss about how the group 2 guys will react with O2 gas, right? How the group 2 guys will react with O2 gas. That is our next discussion, right? How the group 2 guys react with O2 gas, right? This is clear, no? No worries. And keep that in mind, right? So the peroxide and superoxides are made only if you are to heat the stuff, right? Only if you are to heat the stuff. Excess oxygen is needed as well as the heating. Without heating, you can't think of producing peroxide and superoxides, right? Okay, I think it's clear. Right. Okay. Right. Right. Let's come up with the group 2s, how they react with the O2 gas. So first thing to note that is, Lamai, the group 2s are with some low reactivity compared to group 1s, right? Reactivity of group 2 elements are lower or lesser than the reactivity of group 1s, right? So the group 2 guys are smaller compared to the respective group 1 element. The magnesium is smaller than the sodium. So the valence, the ultimate electrons are bit strongly bound to the nucleus compared to group 1 in magnesium compared to sodium. No? So that releasing the electrons ability to get oxidized, that means the reactivity of magnesium is less than that of sodium. So group 2 guys are with some lesser reactivity compared to group 1 guys, right? Okay, so that Lamai, when you are thinking of reactions with O2 gas, right, it is essential to heat. Without heating, the group 2 guys won't react with O2 gas. This is very essential to heat. But when it comes to group 1s, we had seen even without heating, the sodium, potassium, rubidium, cesium, those guys will react with O2 gas, even without heating. Right? To produce the oxides, you don't need heat to produce oxide from sodium, potassium, rubidium, and cesium. Right? But to produce even the oxides from the group 2 guys, you need to heat. Definitely you need to heat because the reactivity is less. If the reactivity is less, reaction rates are less, you can increase them by heating, right? And some reactions at which won't occur at lower temperatures will happen at greater temperatures. So to produce oxides, the ultimate line is you need to heat the stuff. So we can point out that thing like this. All group 2 elements will produce respective oxides when heated with O2 gas. It's essential to heat, right? Then only barium produce the peroxide. Only barium produces peroxide, right? Other than the oxide, when heated with excess O2 gas. So Lamai, not like in the group 1, right? Producing peroxides become harder when it comes to group 2, right? Because the reactivity is low. You won't see the production of superoxides with the group 2s. If it is very hard to produce the peroxide, we can't think of producing the superoxides then. No. More reactivity is needed to produce the superoxides than the peroxides. Right? So superoxides never form with the group 2 elements. Only the most reactive element of the group 2, which is at the bottom of the period of the group, which is the largest element of group 2. So which is the greatest ability to release the electrons, get oxidized. The barium will produce the peroxide. no any other element is capable of producing the peroxide as well. Reactivity is that much more, right? Okay, so if you think of the reactions here, right? Right, beryllium, magnesium, calcium, strontium with O2 gas, all the guys produce only the oxide. If you take the metal as M, all of these will produce the oxide. M coming up as M2 plus, right? 2 plus oxygen state, because the group 2 guys always produce 2 plus cations, right? So when they are heated, right, only the oxides are produced. By the beryllium, magnesium, calcium, and strontium, right? Here M is equal to beryllium, magnesium, calcium, and strontium, right? But when it comes to barium, with O2 gas, it is able to produce the superoxide as well if you are to add some excess O2. If you add some excess O2, barium with the normal amount of O2 when heated will produce the barium oxide. But if you are to add some excess O2 and heated, if you are to add some excess O2 and heated, then barium is capable of producing the peroxide. Peroxide means Ba2 plus and O2 2 minus, right? So 2 plus 2 minus those cancel out. So BaO2. BaO2, right? So barium is capable of producing the oxides as well as the peroxide. So barium is the most reactive element of the group 2, so that it is being able to produce the peroxide as well, right, Nell? Okay, right. So that is how the group 2 guys will react to form the products with the O2 gas, right? So to produce the peroxide, remember, it is essential to come up with excess O2. It is essential to come up with excess O2, right? No? Okay. Right, just copy this stuff, Lama. Right? Barium with normal oxygen producing only the oxide, but with excess oxygen, you produce both the oxide and peroxide mixture, where the peroxide is the major product. Right? Let's have that idea as well. Major product. Right? Right. Just copy this stuff. Right now, okay, let's discuss what will happen. This is what will happen if you expose some piece of sodium to air. Right? This is another thing we need to discuss under this topic, right? Actually, these are the only stuff appearing in your research book, Laman. These are the only things appearing in your research book. But now, what I am going to discuss is actually something which is appearing in your practical schedule, right? So most of the important stuff are there in your practical schedule as well when it comes to inorganic chemistry, right? Not all the things, right? They are at the resource book when it comes to inorganic chemistry, right? So actually, 50% of the stuff of the inorganic chemistry which are going to be questioned in your paper are actually coming from the practical schedule, right? So when we are right constructing this node of S block, mainly we consider both the things. I mean, the things at the resource book as well as the things at the practical schedule as well to come up with a complete node to answer those questions appearing in your papers, right? More confidently, right? Okay, so now I am going to discuss something which is actually appearing in your practical schedule under this block, right? Here, what we are supposed to discuss is actually what will happen. What will happen? It's a kind of a practical, right? You should do in your laboratory, right? In school, right? So now we are going to discuss what will happen if you had exposed some piece of sodium to normal atmospheric air, right? What kind of reactions we would observe, or what kind of reactions we could think of if you had to expose some piece of sodium to air, right? Let's discuss about that thing, right? All right. Reactions which occur when a piece of sodium, right, is exposed to air, exposed to atmospheric air. Right? Let's discuss. So Lamai, don't try to by heart these reactions. Actually, we have 5 reactions here. We could think of 5 reactions happening when you are to expose some piece of sodium to air, right? Actually, don't try to memorize these equations of reactions. Don't try to by heart now. Just think of the scenarios which should occur. Just think of possible scenarios, possible reactions which could occur, right? And then you can predict the products. Then you can predict the products with the use of the knowledge we have gathered at the first half an hour. So if the S block things are involving, if it is a reaction with S block element, the elemental form of this block, it should be a redox reaction. If the compound form of this block species is involved, that is going to be a ion exchange. So you can use that knowledge to predict the products, right? Okay, let's do the stuff. Let's think of what kind of reactions are possible here with this supplied considering environment, right? When it comes to the air, the atmospheric air, right? You had exposed some piece of sodium, right? Piece of sodium. Now exposed to air, right? atmospheric air. So what are the components of the atmospheric air? So you have N2 gas, you have O2 gas as major components. 78% of N2 is there, right? 21% of O2 is there as major components. You have N2 gas and the O2 gas, right? So what else? What else? What else? Right? So you have non-reactive gases. You have non-reactive gases as well. Non-reactive gases. The helium, neon, the noble gas is also there, right? Argon, some consuming amount, 0 point some amount is there. So because these two guys represent 99% of the air, right? 78 and 21 will represent 99% of the air, right? So other gases are in few very small amounts, right? So you have the helium gas, neon gas, argon gas. We are not considering those things because those are non-reactive, right? Not going to react now. The normal gases, right? So as reactive gases, you could come up with some water vapor, moisture. Moisture is also the oldest there, right, in air. And CO2. So CO2 is kind of reactive gas, right? A kind of acidic gas. So we'll react with bases. The CO2 guy is acidic. So we'll react with bases. So these are some components in air which we could think of reactions with sodium, right? Okay, the first thing here is Lamai, sodium is not going to react with N2 gas, Lamai. Even the major contribution to the air, atmospheric air, is from N2. But sodium is not going to react with the N2 gas. We'll discuss that thing at the next section. Why sodium is unable to react with N2 gas. Even such amount of N2 is there. There are two reasons. Right? We'll discuss those things at the next section, where we discuss about the reactions with N2 gas. Right? Okay. So sodium is not going to react with N2, right? Okay. We'll discuss that thing at the next session. Why is that? So let's discuss about the other things. Sodium with O2. Yes, a reaction will occur even without heating. As sodium is such reactive, it will react with O2 gas. So that is the first reaction possible here. Sodium reacting with O2 gas. Sodium solid reacting with O2 gas. Right? So what are products? Just predict the products. Just predict the products. Sodium with O2. Sodium, it's the elemental form. It's the elemental form. The elemental form. So we should think of a redox. We should think of a redox. Elemental form. Think of a redox. Redox, huh? Elemental form. So sodium get oxidized and connect with the anion coming from here. The oxygen's anion is O2 minus, monoatomic anion. Sodium oxidizes as Na plus and connects with the anion of this way. So Na plus and O2 minus, that is Na plus O2 minus Na2O. Right? That is the first reaction possible. Right? Next one. Sodium will react with H2O. Sodium will react with H2O. With the small H's, you know that. Sodium will react with H2O, the moisture. Again, the elemental form is used. Elemental form of the S block guy is used. So redox reaction. So the sodium should oxidize and connect with the anion of this thing. Sodium should oxidize and connect with the anion of this thing. This guy oxidizes and connect with the anion of this thing. NaOH. Na plus and connects with the anion. NaOH. And the H plus here will get reduced. H2. H2 gas. H plus here will get reduced. While this one gets oxidized, there should be something to get reduced. That is the H plus. Right? So sodium is not going to react with CO2, Lamai. At once it is not going to react with CO2. But these basic stuff will react with CO2. As these are basic, those will react with CO2, but not the sodium. Right? So only the sodium will react with O2. With water also sodium reacts. You know that thing with the small H's, right? Right, kind of taking a sodium piece and putting it to the water, you will see some vigorous reaction, some explosive reaction, right? You know that stuff, no? So that reaction, right? Explosive energy is there because the H2 is also producing it. Explosive gas, right? So this so produces Na2O. Not only sodium, it will react, but so produce Na2O will also react with H2O. We know that stuff. Na2O. These are the first phase reactions, these two. Then so produced products will react. First with H2O. Na2O first react with H2O. And Na2O is basic. These guys are basic. As these guys are basic, those will react with the acidic gas as well. As these guys are basic, those will react with acidic gas as well, right? So the Na2O will react with CO2, which is acidic, and that thing will react with this one, NaO. It will also react with, as it's basic, the acidic gas. And these are the possible 5 reactions if you are to expose some piece of sodium to air. These are the first 2 reactions occurring, and these are some reactions by the products of the first 2 reactions. Let's come up with the products here. So this is a S-block compound reacting with H2O. So you can consider the H2O as H plus and OH minus. So this guy these are S-block compounds. So Na plus and O2 minus. So exchange of valencies will give you the product. Exchange of valencies will give you, exchange of ions, ion exchange. Ion exchange will give you the product. So Na plus connected with the anion, O2 minus connected with the cation. Right now. So Na plus with the OH minus, NaOH. S-block compound lang mane, S-block compound lang ion exchange. S-block metal lang redox. Matagal mo ligat? Na plus connected with the anion, NaOH, O2 minus with this cation. O2 minus and H plus is H2. Our reaction is දෙපැත්තම H2O ලියන්නේ. We are not writing the H2 at the both sides. We are not writing one component at the both sides of the equation. Reactions. Hard. Let's come up with the products of these 2 guys as well, right? Right. Let's try to come up with the products of these 2 guys as well. Now these 2 things are a bit special, not following these rules, even though these are considered as some S-block compounds, but not following these rules. So those are special, right? Those are special stuff. We'll discuss this thing, right? And I'll give you some ways of memorizing these 2 guys, right? So actually for this thing, for this reaction, nothing to worry about. I mean, no need of thinking about memorizing methods as well, because just add the stuff together to come up as the product. So you have 2 sodiums, 1 carbon and Three oxygens. Sodium carbonate. Right? And not a hard work to just add the elements to pass the product. Right? So lamai, when learning this stuff, right? When learning this S block chemistry as well as the inorganic chemistry, all the stuff, right? All the inorganic stuff, right? There are two things to master. Right? ඒ කියන්නේ ළමයි මේ inorganic chemistry පාඩම පුරාම කරන්න ඕනේ කාරණා දෙකක් තියෙනවා. මේජර් කාරණා දෙකක් තියෙනවා. මේ දෙක හරියට කරොත් ඔයාලට මේ වැඩේ කරගන්න පුළුවන් ලේසියෙන්. මොකද්ද මේජර් කාරණා දෙක? The two major stuff to study. You have to study the pattern. You have to study the pattern coming up with the reactions. You have to study the patterns coming up with the reactions. The patterns are considered as the rules. The rules are the patterns of nature. The rules are the patterns of nature. We introduce them as theories. Theories, rules, patterns, all are the same stuff. All about the same thing. Right? First, you need to study the rules, or I can say these theories. That means you need to study the patterns coming up with these reactions. Right? Then, knowing the patterns is not enough. Knowing all the patterns won't complete your knowledge. For the complete knowledge, you need to know the exceptions as well. The exceptions from the patterns, the exceptions from the rules, right? There's exceptions from the theories. You should know the exceptions also, right? If you know the patterns really well with the reactions as well as the exceptions, then your knowledge is completed. So now I am discussing about exception. So patterns and exceptions, that is normal stuff, no? Rules and exceptions, right? So in let's think of the normal rules appearing with our country. නේද? නිකන් rules ගැන හිතන්නකෝ. දැන් අපි ලංකාවේ ළමයි වාහන යන්න ඕන පැත්තෙන්ද? වම් පැත්තේ. If you are driving a vehicle, you should go from the left hand side of the road. That is the rule. So that is the pattern we are observing, right? In Sri Lanka, if a foreigner comes, right, and watch the roads of Sri Lanka. If foreigner කෙනෙක් ඇවිල්ලා කටුනායකින් බැහැලා නිකන් අර බලාග පාරක් දිහා බලන් ඉන්නවනම් ලංකාවේ මොකද්ද රූල් එක කියලා නිකන් පැටර්න් එක කියලා අයිඩෙන්ටිෆයි කරගන්න. He will see all the vehicles are going from the left hand side of the road. So he identified that there should be a rule. You'll get that idea. There should be a rule in Sri Lanka that all the vehicles should go from the left hand side. So observing the pattern, right, we can construct a rule. We can think of a rule. Patterns කියන rules එක එකයි තියෙනවා. So but that foreigner may see some vehicles, right? If you are thinking of 1,000 vehicles, 1 out of 1,000 will go from the right hand side of the road as well. නේ foreigner බලන්නේ හරියම දකුණු පැත්තට වාහන හිටපු ගමන් යන්න පුළුවන්. වාහන 1000ක් විතර බලන් ඉන්නකොට එකක් දෙකක් යන්න පුළුවන්. So those are the exceptions. That also exists, right? That also exists in nature. The exceptions are also there in nature. Rules are there and the exceptions are also there. So 99% of the stuff will follow the rules, even in nature, will follow the rules of nature. But there could be 0.01% which won't follow the rules, which are known as the exceptions. But those things also exist. Alright, so exceptions are there. So exception එකක් තිබ්බ කියලා ළමයි ඒකෙන් රූල් එක බ්‍රේක් වෙන්නේ නැහැ. රූල් එක බිඳ වැටෙන්නේ නැහැ. දැන් කවුරු හරි කෙනෙක් නේ ඇම්බුලන්ස් එකක් දකුණු පැත්තෙන් ගියා. නැත්තම් අර අපේ MP මන්ත්‍රීගේ පුතා එලවන වාහනයක් නේද? රෝඩ් එකේ රයිට් හෑන්ඩ් සයිඩ් එකෙන් ගියා. එහෙම කියලා අපිටත් බෑනේ රයිට් හෑන්ඩ් සයිඩ් එකෙන් යන්න. ඔයා රයිට් හෑන්ඩ් සයිඩ් එකෙන් ගියොත් ඔයාව අල්ලගත්තා පොලිසියට ගෙනිච්ච හිර කුඩු දෙන්න. මේවනේ සීන් එක හරි. නමුත් මේ මන්ත්‍රීගේ පුතා රයිට් හෑන්ඩ් සයිඩ් එකෙන් ගියා කියලා ඇම්බුලන්ස් එක රයිට් හෑන්ඩ් සයිඩ් එකෙන් ගියා කියලා ඒක රූල් වයලේෂන් එකක් විදිහට පොලිස් මාම පිළිගන්නේ නැහැ. හරිද? නමුත් ඔයා right hand side එකෙන් ගියොත් ඔයා rule එක violate කරා wow දැම්මා. right කූරු වලින්. ඕකනේ කතාව. හරි. ඒතර ඒ වගේ if you need to survive even with inorganic chemistry you need to know the rules as well as the exceptions. හරිද? එතකොට these guys follow the rules but these two guys coming up with some exceptions, right? So it's not hard to remember this one. As just what you need to do is just add the elements there to come up as the product. Right, let's discuss about this one as well. This is very important reaction, Lavan. This is very, very important reaction, right? This is very, very important reaction. Even though you haven't seen this reaction in the form of NaOH, right? You had gone through this reaction in your O levels. O levels වල ඔයා මේක කතා කරපු ඔයා දන්න reaction එකක් මේ තියෙන්නේ. මේක NaOH එක්ක ඔයාට ටිකක් familiar නැති වුණාට හරිද? මේක ඔයා O levels වල කතා කරපු reaction එකක්. කතා කරපු equation එකක්. මොකක්ද මේ? This is a reaction of CO2 with some strong acid, sorry, strong base with some strong base. Reaction of CO2 with some strong base. හරි? මේ වගේම reaction එකක් ඔයා කතා කරා කොහොමද? මේක ඔයා කතා කරේ දන්නේ නැතුණාට ළමයි. ඔයා මෙන්න මේ reaction එක ගැනව දන්නවා. Even though you don't know about this stuff, right? You know about this reaction, but the reaction of calcium hydroxide with CO2 මේ reaction එක කොහොමද කතා කරන්නේ? කොහොමද මේ reaction එක right ගැන කතා කරන්නේ? What is calcium hydroxide? What is calcium hydroxide? ළමයි calcium hydroxide is what? That is lime water. That is lime water. දැන් මත් මතකද කොහොමද මේක කතා කරන්නේ කියලා? This is the equation, the chemical reaction related to lime water test of identifying CO2 gas. Lime water test of identifying CO2 gas. So what will happen? If you add some CO2 to lime water, first you will come up with some milky solution due to the formation of this calcium carbonate precipitate. This is formation of calcium carbonate precipitate. This is white in color, white PPT. That is what you have observed as milky solution. This is white PPT. So that this could be observed as a milky solution, right? Milky solution. මතකයිනේ? ඊට මොකද වෙන්නේ? If you add some excess CO2, then what will happen? This so produce calcium carbonate and water, that solution will react with the excess CO2. The excess. Then what will happen? That will ultimately produce calcium bicarbonate. Bicarbonates, all the bicarbonates are not going to precipitate aqueous solutions. So calcium bicarbonate, that is a colorless solution. It's a colorless solution. Right now, these are the two reactions involved in the Lime-Moore test. This double reaction one. The two reactions involved in the Lime-Moore test. Right now, so our reaction is analogous to the first reaction of Lime-Moore test. To the first reaction of Lime-Moore test. This one. The calcium hydroxide being a strong base reacting with CO2 acid. NaOH being a strong base reacting with CO2 acid. So that the product will be also analogous to the product here. So with the calcium hydroxide, as you have produced the calcium carbonate, with the sodium hydroxide, you should produce the sodium carbonate. Na plus and CO3 2 minus, CO3 2 minus, Na plus. So Na2CO3. That will be product. So that is how you are supposed to remember this reaction. Right now, sodium carbonate and water. And water is also needed. Water is producing. This reaction is analogous to this, right? Okay, now, so these are the 5 reactions which will happen when, right, a piece of sodium is exposed to air. Now keep that in mind. The final product, the major product of the final product is the sodium carbonate. Final product here is the sodium carbonate, not the sodium bicarbonate, right? This reaction won't occur, right? After producing the sodium carbonate, this reaction won't occur. This reaction, which was happened with the excess CO2, won't occur with this reaction scheme, Laman. Won't occur with this reaction scheme. The reaction which forms the bicarbonate. What is the reason for that? මොකක්ද දෙක reason එක? ඇයි එහෙම bicarbonate හැදෙන්නේ නැත්තේ? Anyone? With a good reasoning why the bicarbonates are not produced like this in the Lime-Moore test? Why the bicarbonates are not produced here? The reason is, to produce the bicarbonates, you need to supply some excess CO2. Excess of CO2. Excess of CO2 is needed to come up with the bicarbonate from the carbonate. CO2 is a kind of acidic gas. What happens is, as CO2 is acidic gas, if you are adding some excess of CO2, the solution becomes more acidic. Acidic means H pluses are greater there. So that those H pluses will combine with the CO3 2 minus and H plus. That is HCO3 minus. The CO3 2 minus will connect with the more added H plus from the added CO2. As it is acidic, it will produce the H pluses from the aqueous solutions. So those H pluses will connect with the CO3 2 minus to produce the bicarbonate. That is how the bicarbonates will produce when you are to add some excess of CO2 with the Lime-Moore test. But that is not possible with this reaction scheme, as we are not supposed to add the excess CO2. The CO2 amount in air is very limited. CO2 amount in air is very limited. This amount is very, very limited. Very limited amount, right? CO2 amount is very limited. So that you won't have excess CO2 to convert the carbonate to bicarbonate, right? That is the reason. So that with the carbonate, the reactions will end. So the final product of when you expose a sodium piece to air is actually the sodium carbonate, right now. Okay, so complete this section. So first write these 5 reactions possible, and then have a note with this thing as well, right? This is the test to identify the CO2. Have that knowledge as well, right? Now, not only with the sodium, but also with other S-block elements. You could think of this with lithium hydroxide, with CO2, it is a lithium carbonate and H2O. With strontium hydroxide with CO2, strontium carbonate and H2O. You can replace any S-block metal other than the beryllium and magnesium to come up with similar kind of a reaction. So you need some strong bases, that is the case, right? Strong bases. So strong bases are the non-precipitating metal hydroxides, or the non-precipitating metal hydroxides are strong bases. So we have to omit the beryllium and magnesium, those because the beryllium and magnesium hydroxides are precipitates. Beryllium hydroxide, magnesium hydroxide, those are precipitates. So those are not strong bases. But all the other non-precipitating metal hydroxides are strong bases. So all of those non-precipitating metal hydroxides, like sodium hydroxide, lithium hydroxide, all the group 1 hydroxides are non-precipitating. So those will come up with this reaction with CO2, as well as the calcium, strontium, barium. Those hydroxides are non-precipitating hydroxides, right? So those will also come up with the same kind of reaction to produce the carbonate and H2O with CO2 gas, right? So this could be this kind of similar reaction will occur with lithium hydroxides, sodium, potassium, rubidium, cesium, all the hydroxides, as well as calcium, strontium, barium, all the hydroxides will come up with this kind of reaction, right? Okay, right. Just complete this stuff, right? At the space given there. So I'll write the final product. Final product here is the sodium carbonate. Final product is sodium carbonate. Remember that as well. Right. Right. Now, shaped. Har. Okay, just complete this stuff. Right. මේ දෙක වෙනම මතක තියාගන්න ළමයි. හරි. දැන් මේක මතක තියාගන්න ඉතින් ගේමක් දෙන්න ඕනේ නැහැ. මොකද what you have to do is just add the elements, right, to come with the carbonate as the carbonate, right? අර මේකෙදි ඉතින් අර just remember the lime mode test reactions involved in there, right? එතකොට ඔයාලට ඒකත් එක්ක knowledge එකකින් ඔයාලට මේක උඩ දාගන්න පුළුවන්. right නේද? හරි. ඉතින් ඔය තමයි what we have discussed is actually how these S-block guys reacting with auto gas, right? And some stuff appearing at the practical schedule also being discussed. Right. Up in the section. Let's move towards the next section there. Right. Next, we have to study about the reactions of S-block metals with the N2 gas. The next elemental gas we are discussing is all about the N2 gas. Let's discuss about that thing, right? Okay. Right. So now we are moving towards the reactions of S-block metals with N2 gas. Reactions of is metals with N2 gas. Right? This is our next discussion. Okay. So before studying this, let's discuss a bit about the N2 gas. Before studying the reactions with S-dot petals, let's first discuss about the nature of N2 gas. Now we know that 78% of the atmospheric air actually contains N2 gas. 78% of the atmospheric air contains N2 gas. What that means actually, what that means? That means the N2 is actually not that much reactive at room conditions. The 78% of N2 is appearing without reacting means it is appearing, that means no reaction with that 78%. Even you have oxygen there, in 21% of oxygen there at the atmosphere, right? Still 78% of N2, that N2 won't react with the oxygens even, right? So N2 can be considered as kind of a non-reactive gas at room conditions. So N2 is kind of a non-reactive gas at room conditions. But that is why the 78% is appearing in air. So if N2 is reactive, if it is a reactive, that won't last no, as 78%. Reactive means consumes. So that you won't be able to see N2 appearing. If it is so much reactive. No, that is what not what happens. 78% of air contains N2. That means N2 is kind of a non-reactive gas at room conditions. Non-reactive gas at room conditions. That is very considerable, right? Not acidic, not basic, neutral, right? So non-reactive. Okay. Then the first question they can ask from that point is actually in A levels as well as in most of the terms, they will ask this question. N2 is considered as a non-reactive gas at room temperature. Explain that statement. Why it is so? Explain that statement. Such kind of question will be asked frequently in term test papers, and they have been asked in A-level paper as well, A-level papers as well. N2 is considered as a non-reactive gas at room conditions. Explain the statement. Why it is so. Right. So you have to come up with if you are to come up with some better answer with full marking points, right? You need to come up with these 2 points. What are the 2 points? The first point is N2 is with a very strong triple bond. N2 is with a very strong triple bond with high bond dissociation energy. With high bond dissociation energy. That should be the answer you need to supply if they have asked you why the N2 is considered as inert at room conditions. Let's examine that answer. Right? It is like this now. For a reaction to occur, the bonds in the reactants should break first, and bonds of the products should be formed. Without that, we can't think of a reaction. To think of a reaction to occur, first you have to break the bonds in the reactants, and then we have to arrange those atoms. We have to rearrange those atoms by forming the bonds of the products. The simple idea is, if the bonds of the reactant molecules won't break, it is hard for a reaction to occur. It is hard for a reaction to occur. With the N2, that is what happens. as N2 gas coming up with a very strong triple bond between the two atoms, between the two nitrogen atoms, very strong triple bond appears, so that it is very hard to break. It is very hard to break. So as a reactant, N2 is not doing its required purpose, right? So as a very strong triple bond is there in the N2, it is very hard to break, so it is unable to participate in reactions frequently. Right now, that is the idea. So you can say the first point, N2 gas is considered as a non-reactive gas at room conditions. Right? If they have asked to explain the statement, if they have asked like that, if then explain statement, so let's come up with the reason here. The reason is this: N2 is coming up with some very strong triple bond with some high bond dissociation energy. Related D value of this thing is very high. See the bond dissociation enthalpy of this triple bond is actually plus 946. You don't need to memorize this number, but it's a very high value now. Normally for a CH bond in hydrocarbons, right, the value comes like 415, 420 kind of values, 400 values. But with the HH bonds, even those values will be there. Even with the O2 gas, the value is 600 kind of thing, kind of value. But here it is 900 something. So very huge value. So very greater heat is needed to break this bond, right, to produce the nitrogen monoatomic species. So very strong triple bond with high bond density energy. That is the reason, right? So reason is N2 is with a strong triple bond. This is the first marking point, strong triple bond. The second marking point with a high bond dissociation energy. With a high bond dissociation energy. That is the second marking point. These two marking points should be there. N2 is with a strong triple bond with a high bond dissociation energy. Just write that in now at the space provided. Right? So now, as N2 is with this kind of a strong triple bond with high bond dissociation energy, it is very hard to break this bond. It is very hard to break this triple bond among the two nitrogen atoms. So that applying heat energy available with the Bunsen burner is not enough. Just only the application of the heat energy from the Bunsen burner is not enough to break this bond. The Bunsen burner alone is not sufficient to that flame from the Bunsen burner alone is not sufficient to supply this huge energy needed to break this bond. So that it needs some help. It needs some help from other method as well to break the bond, break the triple bond of the N2. So that if only some species, some cation with some high polarizing power which will help to break this bond is appearing, then only you can think of breaking the bond with the Bunsen-Burner's energy and coming up with a reaction. Right? The idea is this. Right? The idea is this. Right? So you can write it like this. Right? So let's come up with that idea. So write with me. Due to this, reason, not only the heat energy, not only the heat energy, but also the help of a metal cation, with high processing power. With high processing power is needed to react into and form the N3 minus. Right? Form the N3 minus. Right? The idea is this now. So we need to break this bond. We need to break this bond. We need to break this bond. Right? So if a metal is reacting with N2, we are supposed to come up with the metal nitride. We're supposed to come up with the metal nitride. Right? Metal nitrides are what? Metal nitrides are a combination of the metal and a nitride ion, N3 minus. Oxide is O2 minus. Oxide, the monoatomic anions are coming up with names which are with IDE form at the end. Oxide, nitride, IDE, sulfide, chloride, bromide, iodide, hydride, H minus, F minus, fluoride, see, phosphide, P3 minus. Monoatomic anionic forms coming up with the IDE form at the end of their names. Right? So metal nitride is to produce. So that to produce this N3 minus, right? So you have to supply the heat. Heat from the Bunsen burner is needed, but not only the heat is enough. Not heat alone is enough to put these 3 electrons on top of this nitrogen. Heat alone is not enough. The process needs the help of a cation which is with some high polarizing power. So now when it comes to metals, metals are coming up with metallic lattices. Inside metals, you have metal cations dipped in a sea of electrons. That is how a metal will be constructed. The constituents of the metal. Metal cations are dipped in a sea of electrons. So when it comes to metal, magnesium, calcium, those metals, inside those metals you have metal cations. If those metal cations are with some high polarizing power, right? With high polarizing power, should be high. Q plus O R plus the porosity power should be high. Or one can say charge density. If your metal cation is with a high porosity power or high charge density, then it can attract these electrons towards the metal cation, which will ultimately leads these electrons also to come towards this ultimate nitrogen, right at the corner. As this, if this metal cation is with a greater porosity power, that will polarize this N2 molecule, and these the electrons will attract towards the corner, this corner, and it will help to break this bond by giving these three electrons to this nitrogen to form the N3 minus. That is what happens now. High polarizing power of this cation will polarize this N2 molecule and attract these electrons towards this corner nitrogen, and so that these three electrons will also attract towards this nitrogen, forming the N3 minus. That is how the nitrides will be formed. So to form those nitrides, metal nitrides, it is essential to have a metal cation with high polarizing power. So only the metals containing metal cations with high polarizing power are able to react with N2 gas to produce the metal nitrides. Right? So all the group 2 guys, all the group 2 cations, all the group 2 metals are coming up with good metal cations with high polarizing powers, so that plus 2 charge is there, so polarizing power is high, right? Charge density is high. So that those are capable of producing the nitrides from the N2 gas. So all the group 2 guys will produce the nitrides when they are to heat with the N2 gas. But when it comes to the group 1s, only the lithium will be able to produce the nitride from the N2 gas, because lithium is the metal, or the lithium is the metal with cation which is with a good sufficient polarizing power to polarize this N2, because lithium is the one lamine with the greatest polarizing power in the group 1. When it comes to group 1, all the guys coming up with a +1 charge, but the lithium is with the smallest radius. So when it comes to lithium plus ion, right, only the first energy level appears. Lithium plus means lithium is 2-1 electron configuration, 2 energy levels are there, but when it comes to lithium plus, only 2 is there, that 1 electron is gone. So only the lithium plus contains only 1 electron shell, that is very small, right? Very small atom, only with 1 energy level, right? So very small atom carrying a +1 charge, so charge density is high. So lithium is carrying up with good charge density, better polarizing power, right? That means that is capable of polarizing the N2 and coming up with the N3 gas, N3 minus, sorry, nitride, but not the other group 1s. So that as a summary, we can say with the group 1, from the group 1, only the lithium will react with the N2 gas to produce the metal nitride, lithium nitride, and all the group 2 elements, as those are with greater polarizing powers, will react with the N2 gas to produce the metal nitrides, right? That is the summary ultimately, right? Okay, so just put this picture as well, right? Put this picture as well. React N2 and form lamine. form in 3 minutes, right? And form in 3 minutes. Nitrides, right? Metal nitrides are the ones to produce, right? Metal nitride. Right. Okay, clear? Right? So let's copy the reactions there. What we have written, what we have discussed, just write them. So we can say only lithium from group 1 reacts with into gas when heated, right? Sodium, potassium, rubidium, cesium won't react. Even heated, right? So we can copy that reaction there. Lithium reacting with N2 gas when heated, right? Heating is essential to complete lithium nitride. Lithium, right? Elemental form. This is going to be nitride. Elemental form redox reaction, right? N3 minus, lithium plus, N3 minus, lithium plus, N3 minus. So exchange of valencies will give you Li3N. But this is known as a red colored solid. So this color is stuff lamai red in red color, but not the others, right? Sodium, potassium, rubidium, cesium. Those won't react. Just complete that stuff at this page given there, right? So we can balance this stuff, right? So 1 nitrogen, so there are 2, so 2 is needed here, 6 here. Right? What about the group 2s? All group 2 metals will react with into gas to produce the nitride, metal nitride. Right? So beryllium, magnesium, calcium, strontium, barium, all will react with N2 gas when heated. And produce the nitrides. Be2 plus and N3 minus. Right? So Be2 plus N3 minus. Mg2 plus N3 minus. Exchange of valencies, right? Right? All of these are solids other than the beryllium situation. Other than the beryllium situation, these are solids, right? So ionic solids, no? Ionic compounds, no? This is considered as a liquid, special, no? So that is where the weakest ionic bond. That is where the weakest ionic bond appears, right? A viscous liquid. Sorry, a volatile liquid. Sorry for that. Volatile liquid. A volatile liquid. So ionic bond is weakest with the barium nitride. That is very understood, Lamai, because you know, when the polarizing power is high, the ionic bond strength decreases, right? So this is the one with the greatest polarizing power out of the cations in the group 2, beryllium 2 plus, right, with a plus 2 charge, but the smallest radius, so that the greatest polarizing power appears with this thing, so that the ionic bond is weakest with the beryllium nitride out of these things, right? So ionic bond weakening means the bonds between the particles is weaker now. That means, right, easily will get apart from each other. You can easily liquidize the stuff. So at the room temperature, it's a liquid then, and a volatile liquid. With the supplement of very little energy, it will come to the gas state as well, as the ionic bond strength is very weak here. Right? That is why it is coming as a volatile liquid at room conditions, right? Okay, so complete this stuff as well. So we can balance the stuff. Less balance, right? 2 nitrogens and 3. Yes. Easy balancing, no? Right? Just complete these things. Right? All the things need to be heated, right? Without heating, you can't think of a reaction with N2 gas. Huh? Essentially heat. Essentially heat and have some cation with greater polarizing power. Right. Just complete this stuff. Right. Let's move to the next section, Lama. Or ila section Right. Okay. Right. Now we are going to discuss about Lama. Now we are going to discuss about the, again we are going towards the practical schedule. Right. The things you should know about the reactions with group 2 guys with N2 at the resource book have been discussed, right? Resource book is the knowledge of right? Now we are moving towards the practical schedule, right? The stuff at the practical schedule, right? At the practical schedule, there's experiment. This experiment under this section, right? Which is indicating actually as, right, to confirm the presence of N2 gas in air. Right now we are going to discuss about that thing. This is the practical test which is used to confirm the N2 gas in air. Right? This is used to, right, confirm the existence of N2 gas in air. That is the test, right? This is very important test. Confirm the existence of N2 gas in air. This is a very important experiment now. Why so? The point is, even though we know that, we say that, okay, even though we say that 78% of air contains N2, how to believe that? How to believe? How to confirm that? So that's a fact. Just a fact that 78% of air contain N2. Are you sure? Are you sure that N2 exists in air? N2 එයාවල ඉන්නවා කියලාවත් sure ද? As a fact, even though we are saying that 78% of air is with N2, are you sure whether a single molecule of N2 is there in there? Right? ප්‍රශ්නයක් නේද? You are pretty sure that O2 is existing in air. No worries. O2 එයාවල තියෙනවා කියලා නම් ඔයාට 100% sure. 21% of O2 is there as a fact. But you are sure about that. Why is that? Right? So basically, we do initiate the combustion reactions. Right? So the combustion reactions are possible as O2 is there in air. Right? දැන් ඔයා ඇවිල්ලා ඒ ගිනි ගූරක් මැච් එකක් කරන් ගිනි ගූරක් කරන් පත්තු කරන්න උනත් ඔයාට පුළුවන් වෙන්නේ අපේ ඇට්මොස්ෆියර් එකේ O2 gas තියෙන නිසා. ඔයා ගිහිල්ලා මේ හරි ඔයා ගිහිල්ලා හරි ස්පේස් එකට ගිහිල්ලා where the no O2 gas is there. Right? Just try to get some fire from achieve ගිනි ගූරක් කරන් ගහලා බලන්න ආයි යන්න බැරි වෙන කතාවක් උද හරි right මේ ස්පේස් එකට ගිහිල්ලා ගිනි ගූරක් ගහන්න හැදුවොත් පත්තු වෙන්නේ නැහැ ළමයි right if you are if you are trying to come up with a fire right with a place with some atmosphere without O2 but O2 නැති chamber එකක් හදලා නියොන් ගෑස් හරි මොකක් හරි ඉනර්ට් ගෑස් එක දින O2 ඕක වෙන ගෑස් එක නෑ O2 නැති ස්පේස් එකක් මොකක් හරි වෙසල් එකක් අරගෙන ඒකේ කොච්චර ඔයා දාලා මේ ෆයර් කරන්නද ෆයර් වෙන්නේ නැහැ combustion reaction එකක් වෙන්නේ නැහැ combustion reactions means reacting with O2 to do those is essential to have O2 gas molecules there. So confirmation of O2 in air is not that much hard. All the combustion reactions are possible as O2 is there in air, in our atmospheric air. And if O2 was not there, even we can't inhale. Another problem appears. So confirming that O2 is there is not a deal. Confirming that O2, the second majority in air, is not a deal. But the N2 is a problem. How to confirm that? As it is not going to react normally. With normal circumstances, it is not going to react. It's kind of inert gas at room conditions. So how to confirm that this N2 is there in air? So that experiment carries some greater interest, some greater importance then, right? Okay, so now we are going to discuss about that experiment which confirms the presence of N2 in air. So this is known as a combusting a magnesium rod in air, or ignition of magnesium rod in air. That is what this experiment is named as, right? So the experiment is what? Combustion of magnesium rod in air. That is the name given to this experiment. What we are doing, let's see what we are doing here. So first you take some piece of magnesium. First you will take some piece of magnesium. Let's see, this is a piece of magnesium. Magnesium rod. First you take some magnesium rod and heat the stuff and apply some heat. So we know in air there contains N2 gas, O2 gas, some other gas also there. So what will happen? As heat is applied, magnesium will react with O2 as well as N2. We had discussed those. Magnesium will react with O2 when the heat is applied. We had discussed that reaction when we are learning about the reactions of S-block gas with O2 gas. Just now we have learned that magnesium will react with N2 gas as well when the heat is applied. So magnesium will react with N2 gas as well as O2 gas when you had supplied some heat to this setup, right? So you will come up with some this kind of solid residue. Which contains the product of magnesium reacting with O2 as well as the product of magnesium reacting with N2. When magnesium react with O2, you will produce the magnesium oxide, and when magnesium react with N2, you will produce the magnesium nitride. Exchange of valence is magnesium 2 plus and N3 minus. Magnesium oxide and magnesium nitride will produce, and magnesium oxide is white in color, and this guy is bit yellowish. Right? Those things will be produced by these two reactions. Reacting with O2 gas and magnesium solid reacting with N2 gas. These are the reactions happening with this experiment, right? Let's balance this stuff, right? 1, 2 oxygens are there, so 2 is needed like this. 3 magnesiums are there, right? So it will be like this. Okay. But Lamai, we have a problem here. What is the problem? We have a problem here. What is the problem? The problem is, Lamai, even though we expect that magnesium oxide and magnesium nitrate to produce, so magnesium oxide and magnesium nitride, to produce, we expect that, yes, it will produce. But the problem is how to confirm that these guys are produced, or at least how to confirm that magnesium nitride is produced. That is the problem, next problem here. Because magnesium nitride is not going to shout, hey, I am present here, magnesium nitride, I am present here. He's not going to shout like that. Magnesium nitride shout මේ කෑ ගන්න නැල්ලම හැදුනට පස්සේ නේද? කෑ ගන්නවා magnesium nitride ඉන්නවා ඉන්නකෝ. ඒව නෑනේ. හරිද? This guy is not going to shout like that. Oh, that guy is not wearing a shirt like in Sri Lankan cricket team. Ne? This guy is not going to wear a shirt like a Sri Lankan cricket shirt, right? Where the name of the species is written at the back side. පිටිපස්සේ වැත්ත නේද මැග්නීසියම් නයිට්‍රයිඩ් කියලා ගහපු ක්‍රිකට් ටීම් එකේ ෂර්ට් එකක් වගේ දෙයක් අඳගෙනත් නැහැ නේ මැග්නීසියම් නයිට්‍රයිඩ්. හිමි කියනවා ගේම් වල මැග්නීසියම් නයිට්‍රයිඩ් ඉන්නවා. Right? So there is a problem. We have a problem to confirm the presence of magnesium nitride in this residue. If we are able to confirm that magnesium nitride is there in this residue as produced there, so that will confirm that to produce the nitride, definitely N2 should be there in the air. Without N2 reaction with magnesium, you can't produce a nitride, right? So now our task is to confirmation of magnesium nitride in this residue, right? That will lead you to the confirmation of N2 in air, right? To confirm that, what we are doing is we just add some H2O, some water. Some water is added. Some water is added to this resultant residue, solid residue. Then what will happen? Then lamai, when the water is added, what happens? When the water is added, some kind of a gas will liberate. Some colorless gas will liberate. So what is that? Actually, what is that? See, what is possible there? So actually, lamai, magnesium oxide won't react with water. We'll discuss that thing later at the next session. Why the magnesium oxide is not reacting with water. We'll discuss that thing at the next session, right? But the magnesium nitride will react with water. If a reaction happens like this, how to come up with the products? If you know such a reaction happens, how to come up with the products? This is a compound, this is a S-block compound. So we could think of ion exchange. So you have magnesium 2 plus, N3 minus, you have H plus, OH minus. So what will happen? Mg2 plus connecting with the OH minus to give you the magnesium hydroxide plus N3 minus connect with the H plus. This will give you the NH3 gas. N3 minus H plus. N3 minus H plus, the NH3 gas. See? So that is the colorless gas liberated. Colorless gas with unpleasant odor. Right? So again we have a problem. The same problem appeared earlier. Even though ammonia is going to release like that, it is not shouting like yes, ammonia is present, ammonia coming out. You can ammonia කෑ ගන්න නැහැ නේද? ammonia ත ශ්‍රී ලංකන් team එක වගේ නේ shirt එකක් අඳගෙන නැහැ ammonia කියලා ගහලා පිටිපස්සේ. හරිද? So we have problem. Now we need to confirm the ammonia here. Right? So if we are able to confirm the presence of ammonia here, that will confirm this reaction. That means that will confirm the presence of magnesium nitride here. That will ultimately confirm the presence of presence of N2 in your air. So all depends on confirming this gas as NH3. So what we can do now? So now we can think of reactions or test to confirm the NH3 gas. Now we can think of test to confirm the NH3 gas. Right? Register that thing as well. After that, you can write all the stuff, right? So here, right, I am writing the test to confirm the NH3 gas. Test to confirm the NH3 gas, right? Okay. So here the topic is identification tests. Identification test for NH3 gas. Identification test for NH3 gas, right? Okay. What we need to do is, so the NH3 gas is liberating here. See, let's say that NH3 is liberating like this. That colorless gas. So three chemical tests are available. Three chemical tests are available to identify the NH3 gas. Now, even though all of you know that NH3 is coming up with an unpleasant odor. NH3 is coming up with an unpleasant smell. හරි. දැන් කවුරු හරි කියන්න පුළුවන් හරි එහෙනම් අපි ඇයි සූන බලලා NH3 identify කරගන්න බැරිද? One may ask like that. ඔකට එහෙම විතරද? මේවයි ළමයි. We are not supposed to inhale any gas to identify them in chemical laboratory. Chemistry lab එකේ යන කවදාවත් inhale කරලා ගඳ සුවඳ බලලා gases identify කරගන්න නැහැ. හොඳේ. අපි දන්නේ නැහැ ළමයි NH3 ද වෙන මොන gas එකේද කියලා ඕකේ. If you are not knowing about the gas which is liberating, if you are not confirming that, if you are not exactly knowing which exact gas is releasing, we are not trying to smell that stuff to identify. If some toxic gas is releasing from some compound, what will happen? අර නිකන් horizontal තමයි යන්න වෙන්නේ නේද? හරිද? කෙලින් ඇවිල්ලා vertically ඇවිල්ලා horizontal යන්න වෙන්නේ. හරි? දෙල්ලන්නේ නැහැ හොඳේ. carbon monoxide එක inhale කරා. ඉවරයි. done. හරිද? So that we are not supposed to smell or inhale and identify the gas. So only the chemical tests are available or the visible test. Don't try to inhale. Don't try to smell the gases to identify. හරි. So මොනවද කරන්න පුළුවන්? That few tests are available. The first test, use of Nessler's reagent. Use of Nessler's reagent. So you can have some filter paper with Nessler's reagent. Normally it would appear as some slight yellowish color, right? And you can detect the NH3 gas there. You can detect your NH3 gas there. To that filter paper. So what will happen? So that filter paper will turn brown. Just color this with brown color, the dark yellow or brown. The filter paper with Nessler's reagent will turn to brown if that gas is NH3. With other gases, that won't occur, right? That is the first test, use of Nessler's reagent. The second test, you can use the lid of the Conkex seal bottle. This is also known as test with HCl vapor. Right? If you take the lid of the Conc HCl bottle, right? So if you think of Conc HCl bottle like this, HCl is a kind of a gas. So HCl gas comes here and will be deposited at this lid. At the bottom of this lid will contain some HCl vapor. As HCl gas comes, right, it will deposit at the lid, right? So HCl lid at the bottom side is it some HCl vapor. At here HCl vapor is there. So what you do is you just direct the NH3 gas here. So you have the HCl vapor here, NH3 gas is directed so that this reaction will occur. NH3 gas reacting with HCl vapor. That will produce the NH4Cl. First it will produce at the gaseous state, but as it is a ionic compound, it will convert to a solid. Ionic compounds normally appears as solids in room conditions, as strong ionic bonds are existing among them. So production of NH4Cl solid ultimately happens. That means first NH4Cl gas produces, then it will convert to NH4Cl solid. That conversion of NH4Cl gas to solid can be seen as a white smoke, or white fog, white mist kind of thing. Right? Deposition of NH4Cl gas as NH4Cl solid. Right? This can be seen as white fog or white smoke. Right? Okay. So what other techniques we can use? Let's come up with another one. So I have need some space here, right? This. Sorry. Right? Right? So yes, this is the third technique available to identify the NH3 gas. Third technique. Now you can use the litmus papers, wet red litmus can be used. This is a paper. So now NH3 is considered as the only basic gas available or discussed in the A-level syllabus. NH3 is the only basic gas in our A-level syllabus. Right? We can think of neutral gases, acidic gases. Right? The SO2 is acidic, CO2 is acidic, H2S is acidic. More acidic gases are there. NO2 is acidic. Neutral gases are also there. Carbon monoxide is neutral, H2, O2, N2, not coming up with any acidic basic properties. But when you think of basic gases, that is very rare. Only NH3 is appearing in our A-level syllabus. so that industry is the only basic gas we can say. So it will turn the red litmus, to blue if you direct some industry to the litmus paper. Right, red litmus will turn to blue color. Just color the stuff, right? The color red litmus will turn to blue here. Right now, those are the three methods identification tests available to identify the industry gas. So with the use of one of these methods, you can identify the gas releasing here, right? So as we are able to confirm the releasement of industry like that, the industry is released as this reaction occurred. To occur this reaction, magnesium nitride should be there as the residue. To produce the magnesium nitride, you should have some N2 in your atmospheric air, right? That is how we are supposed to confirm the presence of N2 gas in air with the use of this combustion of magnesium rod in air, that experiment, right now. Okay, just complete this stuff now. So at your page number 8, at that space, you can draw this stuff and write these reactions there, involved reactions. And at the page number 9, the top part is there, some space is there to come up with this section, right? Complete this note now. Right now, with this stuff, right, we'll end the today's session, right? I think මේකත් එක්කම අපි අද දවසේ වැඩ ඉවර කරනවා, right? ඉතින් මම මේ board එක මෙහෙම තියන්න, right? You can copy this stuff, right? හරි, මේක copy කරගන්න, right? ඉතින් වැඩ ඉවරයි, right? So goodbye then, see you next week.